EMC Requirements and Testing, Module 7.2. In this module, we will inspect principles of various test methods and some of the difficulties involved. While performing EMC investigation, different measurement techniques can be chosen, which depends upon where and how the system is intended to be used. As far as possible, the real-life situation should be replicated. However, it is not always possible to do this fully. There can be several reasons for that. Cost is one reason, and size of equipment is another reason. Say, for example, if you want to test an airplane or a big truck or a train, you need different type of test facilities that are normally not available. However, some commonly used test techniques for radiated emission testing is given in the next few slides. So, radiated emission measurements. Some of the techniques used are open area test sites. This is more like a reference test system. Anechoic chamber, transverse electromagnetic cell or TEM cell, reverberating chamber, and Gigahertz transverse electromagnetic cell. Now the open area test site. So this is the most fundamental of all the measurement method. Assume that you have an area that are plain and without any interference from background electromagnetic field. Usually you have to be very far away from cities and other communication areas. Not often very easy to find, but if that is the case, then you can have your equipment to be tested and you can have position your antennas, irradiate the equipment. You can calculate how much are the fields falling on the equipment by taking into account the reflection from the ground. So this is the most standard kind of test site. So there are no particular limitations on the size of the equipments. So you can both do radiated immunity as well as emission testing also can be done using this method, and there are no frequency limitations either. However, it's very expensive to do this type of test because you need to find relatively EM-free noise area far away from other sites, and you need to have the power requirements for conducting the test. So this is not often done. However, open area test sites are used in calibrating the equipments or standard equipments that are tested using the other methods. Anechoic chamber. This is a metallic shielded enclosure lined with microwave absorbing material in the form of carbon impregnated polyurethane foam, and these forms are shaped like pyramids. So basically you have a shielded enclosure on the outside, and this shield will prevent other electromagnetic fields from entering into the test area. So you are blocking out all the external fields. Then the cones, the microwave absorbing materials, will make sure that there are no reflections. If you have just this metallic enclosure, it will reflect electromagnetic fields when you have an antenna inside. But the cones of carbon impregnated material will absorb all the microwaves, and the cone shape is used because it will, even if there are some reflections, that will be again absorbed within the cone, between the cones, and it will minimize all the net reflections that is coming out from the walls. So you can consider that there are no reflections. The term anechoic comes from sound engineering. For sound recording also you use a similar kind of principle. So if you enter into an anechoic chamber and shout, it may feel strange because you don't have any echo. Even for the sound it is quite good. Usually these type of chambers are used for frequencies about 200 megahertz, and there are no real upper limit for frequencies. Up to several gigahertz it can go. However, the lower frequencies are limited by the size of the room. If you want to go lower in frequency, then you have to increase the size of the chamber and becomes more costly. Then another type of chamber is reverberation chamber. This costs much less than anechoic chamber. It is basically a metallic chamber with slowly rotating metal pads to prevent standing wave patterns. So it is called mode mixing. So you can have multiple reflections from all the walls. Then this will be reflected from the paddles, but when paddles are rotating, you are mixing everything. So it is called mixing of the modes. Since no waves are absorbed, it can create fairly high fields for the same power of the antennas. And this is mostly suited for radiated immunity, where you need to use very high fields. It can also accommodate larger equipment under test sizes, EUT sizes, when compared to the TEM cells that you'll be coming to later. It has got fairly high frequency, upper frequency in several gigahertz, but the lower frequency is usually limited. Usually this type of chambers comes above 200 megahertz, because if you want to go lower in frequency, the chamber size has to be much larger and it becomes more costly. Another test equipment is TEM cell, transverse electromagnetic cell. So here the principle is that you create a transverse electromagnetic field in a coaxial structure. We have seen what is meant by a TEM field while talking about uniform plane waves, transmission lines, etc. So this is actually a transmission line, a coaxial transmission line. So this is formed by a rectangular metal chamber. Now towards the end it is tapered, it is covered all along, so it completely blocks all the outside fields, and the tapered sections are terminating into round coaxial connections on both sides. On one side it is for injection, and on the other side it is impedance matching termination for absorbing all the waves so that there are no reflections. So if you look at the coaxial structure, then there is a matching of the impedance from the injection to the cell and the termination. And usually this type of coaxial structures are designed for 50 ohm terminations. You can have 75 ohms also sometimes. So these are the two impedances that are usually used by most equipments. EUT is placed in the middle somewhere. So below this septum, that is the central conductor, or above, you have TEM field, and EUT is subjected to free space condition, that is 377 free space impedance. So due to the confined nature of the cell, you can create very high fields. So this is mostly suited for radiated immunity test. It does not have any low frequency cutoff. You can go very low into frequencies in the megahertz range. However, there can be an upper frequency limitations, because you want to ensure that there is TEM field structure inside, and if you go extremely high in frequency based on the dimensions of the cell, you can have other modes also coming in. So you don't want to go that high in frequency. Still, depending upon the size, you can achieve from megahertz to several gigahertz frequency range in TEM cell. Gigahertz transverse electromagnetic cell. So this is a special case of TEM cell, especially suited for gigahertz range. So if you are mostly interested in extremely high frequency, you can have much smaller size for the cells, and this is kind of a half TEM cell, in the sense that you have a coaxial terminations here. So this is from our lab at KTH. So you have the source connected to the coaxial termination, and the device under test can be placed by opening this window and put it inside. So inside you have a septum, conducting septum, that is terminated, and these are RF absorbers. So what the cell create is a slightly spherical wave, and this is a cross section as taken from here. So septum, so EUT will be under this. So small devices like mobile phones or small equipments can be tested easily using this type of cell. So same comments that are made for TEM cells are applicable for this also. It can create extremely high fields. That is one advantage. Some general comments on EMC testing and some of the measurement difficulties. EMC testing is required to make sure that the devices that are being put into market are tested as per the standards, specified standards, and you want to have repeatability of the test. So that is why we use these standard test methods. So you have something to compare with from one product to the other. However, just because these tests are passed does not mean that the equipment or the device are without any interference or without causing any EMC issues in all kinds of environments, because test environments are often ideal and they may not correspond in reality to the actual situations where equipments are working or devices are working. So EMC investigations are much more complicated, and there are many factors to consider. And standardized testing simplifies those conditions. To give certain examples, any radiating structure or receiving structures can have specific radiation patterns or receiving patterns, and the radiation is non-isotropic. So depending upon how the equipment is placed, you can have different reception or different emission. To some extent, this kind of variations are tried to be covered during the testing by rotating the device under test in various angles and trying to find the most vulnerable radiation lobes. However, it is not foolproof. In anechoic chamber, by mixing the different modes, you are achieving this. In anechoic chamber, by physically rotating the equipment under test, you are achieving this variations in the lobes, radiation lobes. Then there can be several non-linearities which cannot be captured. Say, for example, if you have arcing, say the catenary of a tram or a railway line, you can have a lot of arcs under icy conditions, or due to the mechanical jerk you can have gaps created and arcing. So this is shown over here, current and voltages. So these type of things are very difficult to capture in the laboratory, whereas for the outdoor systems you have those type of situations. In Sweden it is very common during the winter to have icing on the catenary, and due to that arcing of the catenary, which create lot of EMC problems to the trains as well as to the nearby systems, which are very difficult to predict. So that gives you a flair for some of the test methods and some of the standards. Thank you very much.